And I'll also say that I'm presenting from the perspective of someone who did study mathematics and now works in cryptography. That was intentional. I, as a student, knew I wanted to focus on cryptography, but when I mentioned mathematics, that could be pure, that could be applied. There's really plenty of work in the cryptographic space for pure and applied mathematicians. So I'll talk today about a little bit about the quantum threat, which we've already heard about, threatening cryptographic algorithms that we use today. And then I'll discuss a bit about post-quantum cryptography and the future of that and where things are headed. So at NIST, the National Institute of Standards and Technology, I work in a group that's responsible for writing, maintaining, updating cryptographic standards. And sometimes we adopt standards from other standards bodies, sometimes we write new standards of our own. This is a bit of a breakdown of how they're organized. Some of them are based on public key algorithms and symmetric key algorithms. So symmetric key algorithms are when two parties say we want to be able to send encrypted messages back and forth. We must have a pre-shared or pre-agreed upon secret key that we both have, where I encrypt with one key and the decryptor uses the exact same key to decrypt with. So that QKD is an example of a symmetric key algorithm. We heard about that in the previous talk. There's also asymmetric or public key cryptography, where I can publish my encryption key and anyone can encrypt to my key, but only I can decrypt it, hopefully, if I maintain the secrecy of my key well enough. And under our public key suite of algorithms, they're all vulnerable to quantum attacks. So they're all vulnerable to being broken by Shor's algorithm. And we had to make a plan to update our public key cryptographic standards. Why is that? Well, Shor's algorithm performs significantly faster than the classical factoring algorithm. So this is just a graph that shows the disparity. And at the time Shor's algorithm was presented, quantum algorithms weren't fully realizable. They seemed kind of hypothetical. And over time, the development of quantum computing, quantum infrastructure has improved. Here's just a snapshot of some resource estimation that was released by the Global Risk Institute that shows the quantum resources needed to break RSA at the level that would be used today. So you would need at least 4,000 logical qubits, and by their estimations, that mapped to at least 6 million physical qubits. So how long will it take to get there? I don't know. I'd love to poll the audience here just because there's quite a lot of quantum expertise in the room. But all I do know is that millions of physical qubits would be needed to break today's crypto systems. And from what we've heard, we're kind of hovering around maybe 1,000. So there's a bit of time left. Folks were polled. The Global Risk Institute did this nice polling of experts to get their guess on when this full-scale quantum computer that could break RSA 2048 would be realized. And of course, the opinions vary. But what is clear is that cyber systems are going to have to start migrating before the quantum threat is fully realized. Recently, the federal government kind of made a blanket goal of migrating federal systems to quantum-resistant systems or post-quantum systems by 2035. So there's about a 10-year clock that started. Now that NIST is kind of, I guess I'm getting to the punchline first. So our goal was to find some new post-quantum standards. In August, we just released the first 3 post-quantum standards. It's an ongoing process, which I'll talk about in this talk, but now that those first 3 are out, the federal government approach is to start to begin the migration and hopefully have some quantum-resistant algorithms in place by 2035. So how did NIST approach this process? The idea was instead of NIST just saying, we have declared what the new post-quantum algorithm will be and writing that up, the approach was a public, open, transparent process in which there was a call for cryptographic algorithms for the public to submit algorithms to us for consideration of algorithms that are believed to be quantum resistant that we could use for digital signatures and key establishment. The idea is that NIST would merely manage this process, and hopefully we would converge on some community consensus, and in a perfect world, there would be one best in all measures algorithm that was by far better than all the rest, and that's the one that we would pick. That's not really how things turned out. It turned out to be significantly more complicated than previous standardization processes, and we kind of knew going in there wasn't going to be just one single winner. So what do we mean by post-quantum cryptography? In a sense, since we've already heard about Shor's algorithm and Grover's algorithm, you could say that some type of cryptography is believed to be quantum resistant if there's no known application of Shor's algorithm or Grover's algorithm to break it. What's so clever about Shor's algorithm is it exploits this quantum period finding technique that you can use to break integer factorization, and you can use to break the discrete logarithm problem. So a lot of these other active areas that we consider post-quantum don't seem to have some mapping to a period finding algorithm. So there are areas that are based on lattices, codes, systems of multivariate quadratic equations, systems based on hash functions, and isogenies between elliptic curves. So lattices, we did hear a lot about error correcting codes, and they're my favorite, but I decided to talk a little bit about lattices just in case there wasn't any really exposure to that today. So a lattice is just a set of evenly spaced points in some space S. It has some generation set, a basis, and the elements of this generation set are known as the basis when n is the dimension of the lattice. If your basis has n vectors, then your lattice is of dimension n. And here's just a visual toy example of what could be considered a lattice in R2. And the two green arrows would be the basis that's generating this discrete set of points. So one of the hard problems in lattice theory is the shortest vector problem. And that problem is, given some lattice, find one of the shortest non-zero vectors in the lattice. So of course, here we can see that one of the basis vectors is one of the shortest vectors in the lattice. But it turns out that, of course, as we know, there's infinitely many ways that you can represent your lattice. And here are two different bases that generate the same lattice. In one case, you have your basis vectors are slightly closer to orthogonal. In the other case, you have vectors that are quite close and form more of a skew angle. So with respect to these hard lattice problems, when you have a good basis or a better basis, it's easier to solve the shortest vector problem when you have more close to orthogonal vectors that aren't as long. When you have a bad basis, it takes more time to find one of the shortest vectors in the lattice. And you can think of this as applying to cryptography, where if you're given a good basis of the lattice, it's easy for you to find the shortest vector. And you could think of encoding your secret in the shortest vector as shortest vector of the lattice. So you could make your public key a bad representation of the lattice, and your secret is somehow encoded into one of the shortest vectors of the lattice. We also have systems of multivariate quadratic equations. So we're all familiar with systems of linear equations. We know how to solve this in several ways. This is just a system of two equations and two variables. And all of our coefficients live in R, and in fact, the integers, C. A general system of multivariate quadratic equations could involve m equations and n variables, and you would have some variables allowed to be quadratic. And these multivariate cryptosystems generically can be constructed by making the matrix of solutions. So you would make public the matrix of coefficients in the right-hand side of the equation, and then incorporating the solution vector into the shared secret. And the design space can get quite complex when you're working with these systems of multivariate equations. You can think of before when we were looking at examples of RSA or crypto systems where the hard problem is integer factorization. Your public key is just an integer, which happens to be composite with 2 prime factors, and the private key are the 2 prime factors. So your keys are 2 integers or sets of integers. In the case of these lattice problems, your key is really a basis of a lattice, and here your key is some matrix of coefficients. There's also some techniques where you have to hide the function itself, and your keys can take up different forms. But in general, the structure of the keys are different with these different cryptographic problems. So areas of math that comprise post-quantum cryptography outside of, what has already been mentioned, there's also a lot of probability theory when you're trying to prove correctness of an algorithm or the difficulty or the hardness of finding a solution to a problem. There's lots of probability theory involved. Of course, lattice theory, because there are a lot of systems working with lattices. Coding theory, because you can use error-correcting codes. Algebraic geometry, these solutions to the systems. You also have a lot of times working with these isogenies between elliptic curves. Group theory, there have been proposals for different group-based crypto systems. There's all kinds of mathematics. So if the question is, how can we get math incorporated into post-quantum cryptography, it's already there. It does a lot of the heavy lifting in post-quantum cryptography. So there's not a huge learning curve there, just depending on what your area of mathematical background is. But some of the key challenges continue to involve, of course, the security of the algorithms and then the performance of the algorithms. So here's just a snapshot of a table where the bottom row is elliptic curve Diffie-Hellman. So this is an already standardized algorithm that can be broken by Shor's algorithm. And the columns here are showing the size of the public key and the ciphertext, and the size, the time it takes to run key generation, encapsulation, and decapsulation. So for the sake of comparison, you can look at the bottom row as the smallest numbers with regard to bytes. And that's extremely small when you think about how big internet packets are. In practice, you're working with like 1,100 to 1,400 bytes. So you could fit a public key, an elliptic curve Diffie-Hellman key in there with tons of other information and have no problem. The second to last row is what NIST just standardized in August, MLChem or Kyber. It's a lattice-based crypto system, and the public key is about 800 bytes. Ciphertext is roughly 800 bytes, and it does run faster. Key generation encapsulation is faster than elliptic curve Diffie-Hellman, but it's still a huge step up from what we were used to working with for quite a long time. And then the 3 algorithms above, so the first 3 rows of the table, Bike, HQC, and McAleese, these are 3 of the remaining key establishment algorithms that NIST is considering out of this whole standardization process. We started with 82 algorithms, now there's 3 left under consideration. All of them are based on error-correcting codes, and you can still see a pretty extreme performance profile difference. So Bike is based on a more structured code if you compare it to McAleese, which is considered a more conservative design approach to an error correcting or a code-based crypto system. But as you can see, the public key for McAleese is extremely large, 260,000 bytes when you're used to 64 bytes is a huge step up. But what McAleese does have that Bike and HQC do not is a very tiny ciphertext. So something that we have had to consider in this standardization process is how all of the qualities of the different algorithms compare with each other. Of course, security is paramount, but then after security, you do have to consider performance. And after that, if the performance has a strange profile, you try to match it with certain use cases. So this is just an example of how different a lot of these post-quantum algorithms are in practice, and then this doesn't even really mention the security assumptions that go along with each algorithm. So when we were looking at all of the proposed schemes, I mentioned already, we wanted to make sure the algorithms were secure, not only against known quantum attacks, but also against classical attacks. And there are, online I saw a Wikipedia page about the NIST post-quantum process, and for all of the round one algorithms, there's a table of all the attacks that were mounted on the round one algorithms. And I'm pretty sure all of those breaks were just classical attacks. These weren't even quantum attacks. So it's important to understand the security of these algorithms, and that requires a lot of mathematical expertise. Some of them were, most of them were the actual attacks that fundamentally break the system. Comes down to some mathematical knowledge or understanding about how one thing can be applied to another, and it takes a group effort, I guess you could say. Of course, we look at performance and then other properties. So here's a quick timeline. NIST made the initial call for proposals in 2016, and like I said, received 82 submissions. From there, that pool of algorithms was cut to 69 due to some specifications, some requirements that NIST gave. And then from there, we've arrived at round 4. Now that we're in 2024, round 4 may end before the end of 2024 or early 2025. But this was quite a long process. From round 1 to round 2, the number of algorithms was cut from 69 to 26, and then 26 to 15. And then from 15, NIST selected 4 algorithms and kept 4 algorithms under consideration. And then to spice it up, we weren't so happy with the final results of the digital signature process. We had some great schemes. We selected 3 digital signatures, but we still felt that in order to hedge our bets, to really say worst case scenario, if it turns out that there's some unwritten quantum algorithm that can break lattices, what would we do? What would our backup be? So NIST decided to announce a call for additional digital signature algorithms last year. And so that is a concurrent process with the round 4 process. So there's a lot going on. Some observations and experiences is that security analysis benefits from community effort. We've definitely seen attacks from all different types of folks in the field. They could have math background, computer science background, all sorts of backgrounds. A lot of it relies on previous cryptanalytic experience, so it's very important to keep this as open and transparent as possible to make sure everyone is able to chime in. It also takes time. We had an algorithm called Rainbow that was considered a finalist, and it happened to get broken by someone in a pretty unexpected way. And one of our algorithms that had moved on to round 4 was also broken not too long after it was announced that it was moving on to round 4. So there's a lot going on. I'm biased, but it's pretty exciting because you can never know what to expect. So it's pretty easy to sell if you want to get students involved. You have the impact in the sense that this is a national search out of international proposals. And also you have this ongoing tug of war between cryptanalysis and cryptographic design. So considerations, it is possible that some data that's being encrypted today could be harvested for the future quantum computer to decrypt. That's its own issue. So that's part of why I think the government wants to have the migration complete by 2035. But there is a separate project, the PQC migration project, that's housed at the NCCOE, National Cybersecurity Center of Excellence. And they're putting out guidance and things about that. Like I said, for the NIST PQC project, we've already released the first 3 standards. The 4th standard should be released in early 2025. We have 40 additional algorithms that we're analyzing now. And we also have 4 remaining candidates, although one of them, Psych, was broken. So what do I think of the future of post-quantum cryptography? Of course, research-wise, there's plenty of work still needed in development of new algorithms, even if standardization is complete. This is still an emerging area of research in some ways, so there could be developments that haven't been discovered yet. But also the implementations of algorithms. Optimizations will probably continue to happen, but it's important to make sure that the optimizations are secure. A lot of times we see breaks happen because folks optimized in a way that has now jeopardized security because the person doing it did not have a full understanding of what the goals of the algorithm were to begin with. And then, of course, cryptanalysis. I mean, there's always room for cryptanalysis. On the other side, it seems that there could still be, for a lot of work done in the workforce development, curriculum expansion. When I meet with students, sometimes they ask, what should I be studying? And I ask, does your department offer any course in cryptography? Or there's just, of course it's institution by institution, department by department, but there's a lot of room for curriculum expansion and also interdisciplinary coursework, perhaps teaming up with somebody in computer science to do a joint course or something like that. Also, internships are always valuable to students. And there's a lot of cryptographic workshops that offer summer schools or winter schools that are specific for students, for them to come for free and learn about post-quantum cryptography. Also, I screenshotted, SIAM has the Applied Algebraic Geometry annual conference, and in the last one that was in Eindhoven last year, they focused on applications to post-quantum cryptology, elliptic curves, and pairings, although pairings are not quantum resistant, and applications of isogenies. Here's just a link to some of the resources we have on post-quantum on the NIST side. There's lots of other resources out in the wild if you're curious. And I'll stop there. Thank you.